Periodogram. Periodogram is a squared FFT divided by the number of samples in the FFT. And it could also be DFT. So the periodogram is a very old term, and there's a periodogram method of estimating spectra of signals, and it's just an FFT squared. So it's a noise-like signal, so you do square the magnitude because you don't have any phase information. Phase information is useless in a stochastic process, so you only want to look at the magnitude information. So just think periodogram is squared magnitude of an FFT. All right, and the expected value of it is the power spectral density. And so that's why you divide by M. You divide by the length of DFT so that you get the right expected value. Otherwise, the longer and longer the DFT, the larger it grows. You know, there would be a bias equal to the length of the FFT or DFT. And so when you divide out that bias, then you've got an unbiased power spectral density estimator. And so we know that the DFT with zero padding has this async in it, but in the limit, as M goes to infinity, this async just becomes an impulse and it all goes away. All right. But so now the periodogram is not a stable estimate. Its expected value is the right thing, but its variance is high and it does not go down. The variance of the periodogram does not go down as you get a longer and longer FFT. And the way to think about it is that you're just taking the noise and splitting it into bands. So you're taking an FFT of noise and squaring the magnitude, but in each bend, you're just looking at filtered noise. And the magnitude squared of that bend is just the instantaneous amplitude squared at the output of a bandpass filter that just takes the noise and computes 1/nth of its spectrum and puts it out. So you don't have a stable estimate. The thing is fluctuating like mad. You've just split the noise into bands and then squared the magnitude. There's been no averaging, okay? Another thing that's interesting and useful is that the bands are largely independent, to the extent that the bands don't overlap in the frequency domain. If you look at like two far separated bends, then those are separate frequency bands, and so they're independent noise sources in their respective bands. You can use this fact in many calculations. Another way of saying that it's not averaged and that it's not a stable statistical thing is to say that the periodogram at a particular frequency omega is a random variable whose standard deviation is comparable to its mean. And the longer you make the FFT, it doesn't matter. That still becomes the case. It's just a very random thing. So what we have to do is we have to average these things. And that's what's called Welch's method. So this is vocabulary item number 2 here, that the Welch's method is defined as an average of periodograms. And that's what brings down its variance. That's what gives you a stable statistical estimate of the power spectral density. And that's what everybody really uses. So you average periodograms. And you can also just say you average squared magnitude FFTs. That would be totally fine. But I just want to give you the classic nomenclature. So the squared FFT is called the periodogram if you divide by the DFT length. And then if you average a bunch of those together, you've got what's called Welch's method. But fundamentally, you're just averaging squared magnitude FFTs. And the reason there's a trade-off here is because you've always got some segment of data that's finite. So let's say you've got a 100 millisecond duration of S. So you've got this nice tenth of a second S, and you want to get a good spectral estimate of the envelope of that noise, because you're going to synthesize it by white noise through a filter, right? You're doing sine plus noise modeling, and you're trying to estimate that filter. Well, you want it to be a stable statistical estimate because you want your filter to be the right filter. So you want to do a lot of averaging of squared magnitude FFTs. But that means the FFTs themselves have to be very short. And so the more blocks you make so that you can do more averaging across blocks, then the smaller each block. And that means the shorter each FFT. And when you shorten an FFT, you reduce its frequency resolution. So if there's a resonance, if there's a sharp resonance, like, I don't know if I can even do it. If you've got this heavy corner resonance in your noise process, you may not catch it. You may, you'll have probably an over-damped estimate of the resonance. And so the little corner resonance won't make it because you didn't have enough averaging. Well, when you got enough averaging, you didn't have enough resolution to tune that in. So you always have this resolution versus stability trade-off in these situations. So you have to try to figure out what's the optimum block size.